the prior lecture, we learned that the partial pressure of oxygen in the alveoli tends to be around 100 millimeters of mercury, assuming that that person is at sea level and that they are ventilating normally. But now we're going to add some layers of nuance on that. It turns out that not all alveoli are ventilated equally. And in my drawing here, you can probably see that there might be some differences in how much fresh air each of these three alveoli get, simply based on the diameters of the bronchioles. So I have a bronchi that splits into three bronchioles, and I have labeled them A, B, and C. Recall that bronchioles have smooth muscle around them, and the smooth muscle can constrict. When it constricts, we have bronchoconstriction, and you can see that clearly with bronchiole C, whereas bronchiole B is bronchodilated and the smooth muscle is relaxed. Look at what that does to the diameter of the bronchioles. Do you think that's going to affect how much fresh air gets into those alveoli? You bet. So if I have a certain amount of fresh air coming in, it's not going to be evenly distributed between alveoli A, B, and C. Instead, I expect the air to take the path of least resistance the most often. So I expect most of the air will go into alveoli B because the diameter of that bronchiole is so large and therefore does not pose a lot of resistance. A little bit will get into bronchiole A, and a very, very, very small amount will get into bronchiole C. So this is an example of where the alveoli would be getting different proportions of fresh air. So based on this drawing, which alveolus do you expect to have the highest partial pressure of oxygen? B. B will have the highest partial pressure of oxygen because it's getting the most fresh air. And because it's getting the most fresh air, it's also getting the highest infusion of new oxygen. C, on the other hand, is likely to have the lowest partial pressure of oxygen of the three alveoli presented. So after inspiration, we might expect the alveoli to look like this. And instead of writing out numbers for the partial pressure, I simply just put in oxygen molecules to denote how much might be there relative to another alveolus. So now imagine that I'm a pulmonary arteriole and I'm sending my oxygen-poor blood to this area of the lungs. And so I've got sphincters that control access to pulmonary capillaries. If I divert my blood evenly, as you see here, then the blood that goes by B will become well oxygenated, like so. The blood that goes by A will be somewhat oxygenated, and the blood that goes by C will be poorly oxygenated. So this is not the best design. If I want to maximize the amount of oxygen that moves into my blood, then I should send most of my blood to alveolus B. And this is exactly what the lungs do. And the concept of sending most of your blood, your pulmonary arterial blood, towards the alveoli that have the best ventilation and therefore the highest partial pressure of oxygen is known as ventilation-perfusion matching. The term perfusion refers to blood flow. So I want to match my blood flow to the ventilation. In other words, I want to send my blood towards the alveolus with the greatest amount of oxygen. And so the way that the body will do this is it will adjust the tone of these sphincters over here. If I want to restrict blood flow to C, I probably want to completely restrict blood flow to C, maybe reduce blood flow to A, and allow as much blood flow to be as possible, then I'm going to do something like the following. So now the distribution of blood has been adjusted. You can see that over by the sphincters, this set of sphincters constricted somewhat. This one completely relaxed, and this one constricted so hard that the blood vessel, the capillary beds that are served by it, completely collapsed. In fact, this is actually a really interesting property of pulmonary capillaries. If pulmonary capillaries don't have a certain amount of blood in them, they actually just collapse and kind of seal shut until more blood is diverted to them. So the capillary bed serving alveoli C is completely collapsed and really not getting any blood. Alveolus B is getting the vast majority of the blood because it represents the best opportunity to oxygenate the blood. And again, that is because it has the highest partial pressure of oxygen. And therefore, the stronger the gradient, the more oxygen is going to move into the blood. So this hopefully makes sense. Let me show you the book's pictures showing the same thing. Here, it's showing two alveoli, and it's showing pulmonary arterial blood being split evenly between the two alveoli, but we're assuming that these alveoli are equally ventilated. And you can see they both contribute equally to oxygenating the blood, and we get well oxygenated blood. But what happens if one of those alveoli is poorly ventilated? And you can see that here. If it's poorly ventilated and you send equal amounts of blood to each alveolus, then this alveolus does not have a strong enough partial pressure gradient of oxygen to do a good job compelling oxygen to move. And as a consequence, less oxygen gets into the blood by that alveolus, and the overall oxygenation rate, you can see down here, is going to be less, as indicated by the more purple color. So what we do instead is we say, hey, this is the well-oxygenated alveolus, let's send more blood there. And you can see that here. So the follow-up question then is, what controls the smooth muscle around the pulmonary arterioles? In other words, how does the pulmonary arteriole know to constrict some smooth muscle while relaxing others? And it turns out that oxygen itself plays a pretty big role here. Oxygen from here is able to diffuse far enough back to be able to act as a paracrine. So oxygen gas is what determines the tone of the smooth muscle around the pulmonary arteriole. Let's go ahead and write that down. We've seen smooth muscle tone be regulated by another gas, and that is CO2, whereas oxygen gas acts as a paracrine that largely controls the smooth muscle around the arterioles. Recall from a prior lecture that smooth muscle around the bronchioles can be affected by CO2 levels. So this is kind of an interesting dynamic. We have Oxygen gas and CO2 gas are the two gases of significance in the alveoli, and they're both affecting smooth muscle tone. Oxygen gas in the alveolus affects the smooth muscle around the blood vessel, whereas CO2 affects the smooth muscle around the bronchioles. This is a little bit of a busy flowchart, but it kind of describes both of those things working as negative feedback loops, trying to make sure that we never get too much CO2 accumulated in a particular alveolus, and if we do, we're going to go ahead and open that particular bronchiole back up so that we get better airflow, and when we get better airflow, we also bring more oxygen in, and when we get more oxygen in, we then divert more blood to that particular area. So go ahead and pause this. You don't need to write it down for my class, but it does help if you just kind of go through each bullet point and say, yeah, okay, that makes sense. Yeah, that makes sense. The last thing I want to point out is that not all inequities in ventilation have to do with the bronchioles themselves. Sometimes it's just about gravity. So when you are upright and you are breathing, gravity is going to push the air towards the bottom of your lungs. In other words, when air is coming in, it's going to want to kind of naturally get moved downwards, not necessarily up here to the peaks of the lungs. So as a consequence, we actually see better ventilation at the bottom of the lungs than at the top of the lungs. And again, that's mostly just because part of it is your lung anatomy, the proximity to the diaphragm, and some of it is gravity. So if you look here, you can see that the bottom of the lung naturally gets almost 4 times as much ventilation as the top of the lungs. What's interesting to me is, does that mean we send 4 times as much blood to the bottom of the lungs as we do to the top of the lungs? And I want you to look at this. This is how much blood we're sending to the bottom of the lungs per minute, and this is how much we send to the top of the lungs. 1.29 is much greater than 4 times 0.07. So in other words, we really do not send blood to poorly ventilated areas. It's not even a little bit. It's like hardly any at all. And we really do try to make sure that we maximize our ability to oxygenate our blood by sending our blood to the best ventilated areas.